interpolation, you use only 2 data points, but for quadratic interpolation, what you will use is 3 data points. Okay. And the function that you can approximate will represent in terms of C0 plus C1 x minus x naught plus C2 x minus x naught times x minus x1. Okay, and it still derived in the same manner. So at x equal to x naught, what you get if you plug in x equal to x naught to this function, you get f x naught will equal to c naught plus c1 x naught minus x naught, which is actually 0, plus c2 x naught minus x naught times x naught minus x1. Of course, it is 0. So we get fx naught equal to c naught. This is the first equation. Okay. And for the second equation, it is derived from x equal to x1. So fx1 that's equal to c naught plus c1 x1 minus x naught plus c2 x1 minus x naught times x1 minus x1. This term is 0. So from here, what you get is fx1 thus equal to c naught plus c1 x1 minus x naught, and from here c1 thus equal to fx1 minus c naught, right? But we already know that c naught equal to fx naught, so here is fx naught, and it will divide by this term, so it will divide by x1 minus x naught. This is the second equation, right? And also at the x equal to x2, you plug this term into this fx2, right? So what you get is actually after you replace fx2, right? So it would be fx2 equal to c naught, which is actually fx naught plus c1, right? c1 is actually these terms. So c1 is fx1 minus fx naught and divided by x1 minus x naught, right? Times with x2 minus x naught plus c2 times x2 minus x naught times x2 minus x1. Okay. From this equation, if you arrange, you will get the form. Actually, this form is created to support the general form of the Newton divided difference. So the form that you will get would represent in terms of fx2 minus fx1 divided by x2 minus x1 minus fx1 minus fx0 divided by x1 minus x0, and this equation is divided by x2 minus x0. Okay, so assume that I give you an example that we would like to approximate a function from these three data points: x naught equal to 2, y naught equal to 0.2239, x1 equal to 3, y1 equal to minus 0.2601, and x2 equal to 4, y2 equal to minus 0.3971, and we would like to know what at x equal to 3.2 what y should be. Okay, so basically you can approximate the function of these three data points in the quadratic function form. So it is c naught plus c1 x minus x naught plus c2 x minus x naught times x minus x1. Okay, and from here we know from the first equation that c naught equal to f x naught, so it equal to 0.2239, right? This is y naught here, and c1 is actually compute from fx1 minus fx naught divided by x1 minus x naught. So from here we can plug in this value to this formula. So what we get is minus 0.2601, which is y1, minus this y naught, which is 0.2239, and divided by x1, which is 3, minus x2, minus x naught, which is 2. So what we get is c1 that's equal to minus 0.4840. Okay? And the last term is c2. Right? So for c2, we can use the formula that we write before. So it is fx2 minus fx1 divided by x2 minus x1 minus with fx1 minus fx naught divided by x1 minus x naught, and the whole of this equation is divided by x2 minus x naught. Okay, from here we substitute fx2 is y2, right? And y2 is actually minus 0.3971. So from here we write down minus 0.3971 minus with fx1, which is y1. y1 is actually minus 0.2601. So this is the minus 0.2601, and from this term we divided by x2, which is 4, minus x1, which is 3, right? And it's minus with fx1. fx1 is actually y1, right? So it's this term. Okay, so I would write it down, which is a minus 0.2601 minus with fx naught. fx naught is 0.2239, right? And this term divided by x1 minus x naught, which is 3 minus 2. And after that, we divide by x2 minus x naught, which is 4.2. So from here, if we do the calculation, we get C2 that's equal to 0.1735. Okay, now we know C0, we know C1, and we also know C2. So Fx that's equal to C0, which is 0.2239 plus C1. C1 is minus 0.4840 times with x minus x naught plus C2, which is 0.1735 times with x minus x naught times x minus x1. Okay. Now, if you want to know what fx is at x equal to 3.2, you just substitute x equal to 3.2 to this position, and then you calculate. So the result at fx, which is equal to 3.2, what you get is y or fx would equal to minus 0.3153. And that's all for the quadratic interpolation. Alright. The next part is the general form of the Newton divided difference. So if we try to increase the order of the approximation, we already start linear, we already start quadratic, and for the generalized form, so we learn to use the polynomial interpolation. And for the polynomial interpolation, the form we represent in terms of fx equal to c0 plus c1 x minus x0 plus c2 x minus x0 times x minus x1. And of course, if you want a higher order, so you can add like c3 times x minus x0 times x minus x1 times x minus x2, and then you can add more terms, right? So until the n order, like cn x minus x0 times x minus x1, and you multiply it until x minus xn minus 1, right? Okay. So Newton divided difference, try to create a form that you can use it simply. So at C0, you find the last two interpolations, which is linear and quadratic. You see that at C0, it is the fx0, right? And also C1. So if we write in the form of f of the x1 and x0, where f xi, xj equal to f of xi minus f xj divided by xi minus xj. Okay, this is C1, right? So from here, if you find f of x1 comma x0, what you get is f x1 comma x0. So from this formula, you get f x1 minus f x0 divided by x1 minus x0. So it is the same as we derived previously. And for C2, okay, C2 have the form of f of x2 comma x1 comma x0, where f xi, xj, xk will be represented in terms of f of xi comma xj minus f of xj j comma xk, and we divide this function by xi minus xk. So if we try to calculate this term, what you get is f of x2, x1, x0. So we get f of x2, x1, right? Minus f of x1, x0, right? Divided by x2 minus x0. And from here, if you use this formula, okay, to represent the relationship between this term and this term, so f at here is x2, x1, x0, thus equal to f of x2 minus f of x1 divided by x2 minus x1, okay, and minus with f of x1 minus f of x0, and here is x1 minus x0, and we divide the whole equation with x2 minus x0. So this is the formula that we derived before, right? So this is almost the same, right? fx2 minus fx1 divided by x2 minus x1, and minus with fx1 minus fx0 divided by x1 minus x0. This term also here, okay. Alright, so this is a general form for polynomial interpolation. And of course, you can calculate the higher degree, for example, as Cn. It is like f of xn, xn minus 1, x1, x0. Okay? So from here, it comes from f of xn, xn minus 1, x1. Right? Minus with f of xn minus 1, xn minus 2, x1, x0, right? And the whole equation is divided by xn minus x0. Okay. So you may think that it is hard to memorize all the formula, but I'm gonna show you the way that how do we create the technique actually help for using the Newton divided difference. So assume that you have a data at the point I, which is equal to 0, you get x0, and here you get fx, which is fx0. So at the point I equal to 1, you get x1, here is f of x1, and at the at the third point, which is at I equal to 2, you get x2 and f of x2, and also at the I equal to 3, you get x3 and f of x3. Right? So from here, you can use these two equations to calculate f of x1, x0. Right? So, and also from here, you can use fx1 and fx2 to calculate f of x2, x1. So at the first round, you can calculate here f of x3, x2, right? This is the first round. And then what you can do is that you can calculate f of x2, x1, x0 by using these two values. And also you can calculate this term, okay? So you get x3, x2, x1 from these two values. And the next round, you use these two values to determine f of x3, x2, x1, x0. Okay, and you can continue like this repeatedly until the order that you want. So this is the whole idea of the Newton divided difference. And in the next lecture, I will talk about the Lagrange interpolation.